The last section we look at is 7.1, Introduction to Discrete Probability. So what is probability? Well, it's a way to measure how likely a future event is, and it goes from 0 to 1. So probability, it's always a number. It has to be between 0 and 1. So 0 means this future event is certain not to happen. Small numbers mean it's unlikely. 1/2, so that's 50-50. So tossing a coin and getting, say, heads, that has probability 1/2 if the coin is fair. 1, probability 1, that means it's something certain to happen. And numbers close to 1 are more likely. For example, if your phone says there's a 90% chance of rain, well, 90%, that's 0.9, so that's close to 1, so that's very likely. So yeah, you need an umbrella. Okay, so that's the idea, probability. What is discrete probability? Yeah, that's a kind of a simpler situation where we can actually mathematically calculate probability exactly. For example, in rolling dice or card games, things like that, we can make calculations. And all this work is a nice application of the work we did in sections 2.1 and 2.2 on sets, and in chapter 6 on counting. Okay, so we'll see how sets and counting are connected. Alright, so let's look at a simple example to start with. So rolling a die. A die, yes, that's the singular. The plural is dice. So 2 dice, 1 die. Okay, so a die is just a cube with kind of rounded edges to make it roll easier, and it has 6 sides labeled 1 through 6. What is the probability of getting a 5 or a 6? Okay, so you just roll this die once, look at the number that comes up. What's the probability that it's a 5 or a 6? Well, yeah, when you're rolling, there are 6 equally likely possibilities, and 2 of those are what we're interested in, so getting a 5 or a 6. And the way it works is, so to calculate probability, it's just going to be 2 divided by 6. Okay, we'll see a formula in a minute, but just these 6 possibilities, and we're interested in 2 out of the 6. So that's this fraction, 2 over 6, which is 1/3. So that means there's a 1/3 chance, or as a percent, it's a 33 1/3% chance of getting a 5 or a 6. Yeah, there is another nice way to think about that. Yeah, if you roll this same die 100 different times and then count up all the times you got a 5 or a 6, then you could roughly expect that to be close to 33. Okay, so 33 out of the 100 rolls, you're getting a 5 or a 6, roughly. So it won't be exactly, well, it can't be 33 and a third, but it, yeah, we're getting into some sophisticated ideas here, expected values, laws of large numbers, but you see the idea. All right, so that's a good example to have in mind. So let's look at our definitions and the actual formulas. Okay, so in this, this probability has its own language. So in probability, an experiment just means something like rolling a die, or tossing a coin, or getting dealt a hand of cards. It's it's something that's going to happen in the future, and it has a set of possible outcomes. Okay, so the different things that can happen. The sample space is just the list or the set of all possible outcomes of the experiment. Okay, so the sample space, yeah, it's a funny name, but it's you're just looking at every possible outcome, every possible thing that can happen in the experiment. And an event is a subset of that sample space. Okay, so you're focusing on some certain, some maybe outcomes that you're interested in. Okay, so in example 1, okay, when you roll a die, there are only 6 possibilities, so these are the outcomes, and the sample space is the set of those 6 numbers. Okay, so this is where sets come in. The event E in example 1, so we were interested in rolling a 5 or a 6, so E is the subset 5, 6. Okay, so we have outcomes, sample spaces, events. And here's the key definition. So here's the formula for probability. Suppose a sample space S of equally likely outcomes. All right, that's important. So we need the outcomes in the sample space to be equally likely to happen. Okay, so each of these 6 numbers is equally likely to show up when you roll the die. Let E be a subset of S. That's the event. Then the probability of that event happening, we have this notation, P of E. So that's the probability of E happening is equal to the cardinality of E divided by the cardinality of S. All right, so we're dividing like in the example. So on the bottom, it's the number of elements in the sample space, and on the top, it's the number of elements in the event. The elements here are just the outcomes. So this is like a function, so it's the probability of the event. So for example 1, it was 2 divided by 6. All right, so it's a simple formula. Okay, you can see where the counting is coming in. We need to count the number of elements in each of these two sets, and then just divide. Okay, so nothing too difficult, except, well, we'll see in our examples the counting can get a bit tricky. But example 2 is easy. So again, roll a die. What is the probability of not getting a 6? Okay, so it's a sample space. The numbers that can come up on the die, 1 through 6. What is the event E now? Well, not getting a 6. Not getting a 6 means getting 1, 2, 3, 4, or 5. Okay, so this time E contains 5 outcomes. So the probability of not getting a 6 is 5 over 6. So that's quite likely. If you roll a die, what's the probability of rolling a 7? Well, what subset of the sample space is that? Well, it's not in the sample space, so the event would be the empty set. 0 elements. All right, so the probability of rolling a 7 is 0 over 6. That's 0. Certain not to happen, or impossible. Okay, so rolling a 7 is a probability 0 event. And at the other extreme, what's the probability of rolling a number 1 through 6? Well, if the event is rolling a number 1 through 6, there are 6 ways for that to happen. So the probability is 6 over 6, which is 1. So that's certain to happen. You have to get a number 1 through 6 when you roll a die. Okay, so you can see these two going back to our graph. Probability, it has to be a number between 0 and 1. It can't be negative, it can't be 1.1 or anything higher than 1. And just a remark here, our probability formula, cardinality of E over the cardinality of S, it's only valid when the sample space outcomes are equally likely. So we have this is part of the definition. For example, if our die had been tampered with, say by adding a small weight to one of the sides, that would mean that different numbers are not equally likely. So we can't use the formula in that case for if the die is not a fair die. Okay, example 3. You flip a coin 10 times. What is the probability of getting tails every time? Okay, so we're tossing a coin. It has to come up heads or tails. So the experiment here is flipping this coin 10 times. The outcomes are the results of the flips. So one possible outcome is, so the first time you got a head, then tails, 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 heads, tails, heads, heads, tails, tails. So this is one possible outcome from the 10 flips. Okay, now we're getting into some counting. Okay, so the sample space is pretty big, so you can see there are lots of different results you could get. How many? Well, by the product rule, yeah, so think of how many ways can the first coin land, well, either heads or tails. That's 2 options. 2 ways for the second flip, 2 ways, so it's by the product rule, it's just 2 times 2 times 2, so 2 to the power 10. 1024. So the sample space has this many elements. Okay, so what's the event E for this question? Well, we're interested in the case where we get tails for every flip, so 10 T's. How many ways can that happen? Well, this is just one of these 1024 outcomes. So the cardinality of E is just 1, all right, just one way to get 10 tails. So the probability of flipping a coin 10 times and getting 10 tails is 1 divided by 1024. So yeah, you can see, you could try it. It's very, very unlikely, like a 0.1% chance of that happening. And that's a good way to think of unlikely events. If for example, if you're looking at say scratch cards, you can read the probabilities on the back. So if there's a 1 in 1,000 chance of getting a prize, then you could think that's roughly the same as tossing a coin 10 times and getting whole tails, so pretty unlikely. Yeah, so don't play scratch cards is my advice. All right, so in the book here, there's a nice discussion about the history of probability. It goes back to the Renaissance, 1526 in Italy, Cardano. Pascal, who we met earlier. Alright, here's the key formula again. The cardinality of E over the cardinality of S. Example 1 here. An urn contains 4 blue balls and 5 red balls. What is the probability that a ball chosen at random from the urn is blue? Alright, so the experiment is picking a ball out of this urn. Okay, there are nine balls, so that there are nine outcomes. So the sample space is size 9. We're interested in choosing a blue one, and there are four ways that can happen. So So the probability of getting a blue one is 4 divided by 9. So yeah, so it's more likely you'll get a red one that has probability 5 over 9. Okay, so slightly less than 50-50 to get a blue one. Example 2, what is the probability that when 2 dice are rolled, the sum of the numbers on the 2 dice is 7? Yeah, so for 2 dice we can get a 7. For example, you could get roll a 3 on the first and a 4 on the second, then the sum is 7. Yeah, so now we're definitely counting. So if you roll 2 dice, what is the how big is the sample space? How many possible outcomes are there? Okay, well, yeah, we have these 2 dice. So the first die there has 6 possibilities, and the second die has another 6 possibilities. So by the product rule, that's 36 equally likely possible outcomes. If you made a list, you could do, say, a 6 by 6 table. That'd be 36 outcomes. Oh yeah, here's Mr. Cardano. Okay, so the number of elements in S is 36. How many outcomes correspond to the sum being 7? Well, yeah, now we're counting again. So you could get a 1 on the first die and a 6 on the second, or a 2 and a 5, 3 and a 4. Okay, so you can see there are 6 ways to get 7. So the cardinality of E is 6. And the answer is 6 divided by 36. Cancel 6's, that's 1 over 6. Okay, so the probability that you get a sum of 7 from rolling 2 fair dice is 1/6. So fairly unlikely. Example 4 looks at a lottery. So, yeah, let's say this lottery has 40 numbers, and to win you have to pick the correct 6. Okay, so what's the probability of winning this lottery? Okay, yeah, so I'm sure you've seen this on TV. So they have balls labeled 1 through 40. Then there's a drum or a machine, and six of those balls come out randomly. So, and your ticket, or you choose 6 numbers, and you get the prize, you get the millions if your 6 numbers match their 6 numbers. All right, so how many ways can you have 6 numbers coming out of 40? All right, so we're choosing 6 out of 40. First thing to figure out, does the order matter? No, so the order doesn't matter, you just care about the numbers. So the order they come out of the drum doesn't matter. Okay, so this is a combination question. So it's C40, 6. So this combination, this is the total number of outcomes here is this. We can work it out. Yeah, this formula, so some big numbers, but it's 3,800,000 and some thousand. And only one of those is the winning combination. So the probability of winning this lottery is 1 in 3 million, close to 1 in 4 million. Yeah, so 0.000, lots of zeros, 26. Yeah, and in fact, most lotteries, they have a much bigger number of balls, so maybe 60. So that makes the odds even smaller of picking the right 6. Yeah, there are often smaller prizes if you match 5 or 4, so you could calculate those too. All right, let's take a look at card games. So yeah, maybe take out a deck of cards and have a look. Okay, so we're not using the Joker, but apart from that, there are 52 cards. You've got aces, 2, 3, up to 10, and then also jacks, queens, and kings. So 13 different kinds. And each kind can be in one of 4 suits: clubs, diamonds, hearts, and spades. Okay, so altogether 13 times 4, that's 52 cards in a pack or in a deck. And lots of card games. Example 4. You pick a random card from the deck. What is the probability that it is a jack or a 4 of clubs? Yeah, here we mean any kind of a jack in any suit or a 4 of clubs. Well, yeah, there's only one 4 of clubs, but there are 4 jacks. Okay, so we're looking at randomly picking one of these 5 cards. What's the sample space? Yeah, so this experiment, we're just picking a random card out of the 52, so there are 52 possible outcomes. So cardinality of S is 52. Cardinality of picking one of these is 5. So that's the probability, just 5 over 52. And as a decimal, that's 0.096. So 9.6 approximately probability of picking a jack or a 4 of clubs. All right, so yeah, again, the same formula. We're just in this working with cards at the moment. And yeah, so then for example, yeah, looking at poker hands, then it can get a bit trickier to do the counting. Example 5, find the probability that a 5-card poker hand has 3 cards of one kind. Again, these are the kinds, so maybe it has 3 sixes or 3 jacks, 3 kings. What? Of course, they have to be at different suits, but what's the probability of that happening? Okay, so putting it into our setup so that, yeah, the experiment here is getting dealt 5 random cards from the deck. Does the order matter? No, you could, put the cards in order when you're holding them. So the order you get the cards in doesn't matter. So it's so the number of possible hands where you don't care about the order, that's a combination csi30, 5. Okay, so how many 5-card poker hands are possible? 2,598,960. Okay, that's csi52, 5. So that's the cardinality of S. That's the bottom number. Okay, for the top number, we need to count how many of those have 3 cards of the same kind. Yeah, so these could be the cards in your hand. So this is what we like to count. Yes, say 3 queens and then 2 other cards. Yeah, so interpreting the question, we're not including 4 cards of the same kind, so only 3. So these can't be queens. Something else. Okay, so let's try to count how many ways we can get 3 cards of the same kind. Okay, so as usual, we're using the product rule. Remember, you can think of the product rule as like a series of tasks. How many ways to do the first times how many ways to do the second. So if you're trying to construct this a hand like this, how many ways to do it? Well, first, so here we have queens, but there are 13 different possible kinds. All right, yeah, we could write it csi13, 1, but it's 13 different ways to choose the suit of the 3 of a kind. Then, once you've chosen the kind, then there are different. You're only choosing 3 out of the 4 queens here. So it's a combination. You're choosing 3 from 4. You don't care about the order. So basically, you're leaving out 1 queen, and there are 4 ways to do that. Okay, so there are 4 ways to choose the 3 cards of the same kind. All right, so we have 13 times 4. That's 52 ways to organize this piece. And how many ways can we finish the hand? Okay, we don't want any more queens. And we're choosing two more cards. We don't care about the order. So if you exclude the 4 cards of this first piece, say the queens, that leaves, out of the 52, that leaves 48 cards, and we're choosing 2 of those. So there are this many ways, 1,128 to finish the hand. Alright, so again, 13 ways to choose what kind of card is repeated, 4 ways to choose that kind, and then this many ways to finish the hand. And so altogether that's 58,656 ways to get hands that have 3 of the same kind. Alright, so that's our top number. So the probability is 0.02257, so roughly a 2.26% chance. Yeah, so not very likely. Yeah, usually if you get dealt a poker hand, yeah, you might get a pair, but it's much less likely to get 3. Yeah, note that we didn't exclude the possibility that the last 2 cards are the same. So yeah, we're including full houses in this calculation. So we're including, say, 2 3s here. Of course, in poker, that's worth a lot more. That's a full house. Okay, yeah. So you can see it is kind of complicated, but we're just using our techniques, the product rule, and combinations. Yeah, the order is not important in these poker counting, at least not here. Okay, example 5 in the book. Find the probability that a hand of 5 cards in poker contains 4 cards of one kind. Alright, so that's similar. Okay, so the same bottom number. And now we're choosing, okay, so the kind, where we have the 4 cards, 13 ways to pick the kind. Then, yeah, choosing 4 from 4, there's only one way to have all 4 cards. And now there's only 1 card left to choose, so 48. So choosing 1 from 48, yeah, there are 48 ways to pick the last card. Alright, so yeah, so that's just 13 times 1 times 48. So yeah, that's a much smaller number on top. So it's much less likely to get 4 cards of the same kind than 3 cards. 0.00024, so just a 0.024% chance. Yeah, example 6, yeah, this is the full house case I mentioned. So what's the probability of getting a full house? So that's 3 of one kind and 2 of another kind. Yeah, so different ways to do it. One way is to so you first pick the two kinds that are going to be repeated. Say queens and threes, so 3 queens and 2 threes could be your full house. But now the order does matter. So if you're doing the queens, so if you want, say, 3 queens, so doing the three of a kind first, and then the second is going to be the 2 of a kind, the pair. So choosing the kinds is a probability. It's a permutation. So it's a permutation number. Choosing 2 from 13, where the order does matter, because you're doing the threes first, 3 of a kind first, then the pair. Okay, so P13, 2 ways to pick the suits. To pick the kinds. Then you're choosing 3 from 4 to get the 3 of a kind, and then choosing 2 from 4 to get the 2 of a kind. Okay, now the order does not matter. Okay, so I hope that makes sense. Again, the product rule. So that's 3,744 ways out of the 2.5 million to get a full house. So that's a very small number, so that's very, very unlikely. So that's why it's worth a lot in poker. And one more here. So no cards this time. We're back to kind of lottery balls. What is the probability that the numbers 11, 4, 17, 39, and 23 are drawn in that order from a bin containing 50 balls labeled 1 through 50? 2 parts. A, if the ball selected is not returned to the bin before the next ball is selected, and part B, if the selected ball is returned to the bin each time. Okay, so for part A, where we're not returning the ball, so how many possible outcomes? Well, there are 50 outcomes for the first drawing. Okay, so one of these 50 balls comes out. We're not returning it, so now there are 48 balls can come out for the second drawing. 48, 49, 48, 47, 46. Alright, so yeah, this is just a just by the product rule, it's this many, 254 million ways to for these for 5 balls to come out. And if you want these exact numbers to come out in this order, there's only one. That's only one out of these 254 million outcomes. So the probability of getting this exact sequence is really small. I think This is the smallest probability we've seen so far. It's 1 divided by 254 million. Yeah, this is sampling without replacement, so we're not putting the ball back in. Part B, if you put the ball back in each time, then it's 50 times 50 times 50 times 50 times 50, so 50 to the power of 5. Okay, so more outcomes if you do replace the ball. And if we're still looking for this sequence, then now it's, there's only one way that can happen. So that's 1 out of, this time 312 million. All right, so even less likely. This is sampling with replacement. So so these, if you're trying to choose numbers, and if the order does matter, then that makes it even less likely to get the right combination. Okay, so just one more topic, probabilities of complements and unions of events. I probably should have drawn this earlier. So back in example 1, we can make a nice picture. So remember our work in sets. We have these Venn diagrams. So we can use a rectangle for the universal set. So that's, in this case, that's the sample space. So all possible outcomes. So for rolling a die, there are 6 possibilities. So six elements. And then the event E in example 1 was rolling a 5 or a 6. So that's this subset. So this is E. And you could look at other subsets. So you could have E1, E2, make Venn diagrams. Okay, you remember the complement of a set. Say a set T means all the elements in the universal set that are not in the set T. And use the notation. Just put a bar above it for the complement. So the complement of an event is just the sample space minus that event E. Okay, so for this example, it's just everything that's outside E. So in this case, E bar. And the complement is just all these other possibilities. One, 2, 3, and 4. All right, so the complement, it just means that the event E did not happen. Yeah, here's the complement. So in general, so what's the probability of the complement? Well, as a simple formula, it's just 1 minus the probability of the original event, E. So the probability of a complementary event is just 1 minus the probability of the event. And that's easy to prove. So the number of elements in the complement is just the number of elements in the sample space minus the number of elements in the event. So here it's 6 minus 2. Okay, so that's the number of ways that E bar can happen. And divide by the cardinality of the sample space, and just simplify. So it's 1 minus this, and this is the probability of E. Alright, so it makes sense. Example 6, what is the probability that a 5-card poker hand does not have 3 cards of one kind? Well, in the last example, we found that the probability of getting 3 cards of one kind is this number, 0.02257. Alright, so that's the probability of getting 5 cards of one kind. For this example, we need the complement, so the probability of that not happening, and that's just going to be 1 minus the probability of it happening. So 1 minus this is 0.97743. Alright, so we're just using the formula. So that means a 97.74% chance of not getting 3 of one kind. So very, very likely. Okay, so yeah, so we're just saying, yeah, if the probability of something happening, if you know that, then the probability of it not happening is just 1 minus that. Alright, and just one more thing. Yeah, the inclusion-exclusion principle for sets says that the number of elements in a union is equal to the number of elements in each set minus the number of elements in the intersection. Okay, so we can use this formula when we're looking at 2 events, say E1 and E2. And for our formulas, yeah, then we just divide both sides by the number of elements in the sample space. Okay, so that leads to this formula. So the probability of the union of 2 events is equal to the probability of each event separately, the sum, minus the probability of the intersection, which means the probability of both events happening. And the union here means, yeah, the probability of E1 happening, or E2, or both. Alright, so yeah, this is a famous formula in probability. Let's see an application. So example 7, pick a random card from the deck. What is the probability it is a diamond or a king? So let's break this into 2 events. So let's say E1 is the event of getting a diamond. Let E2 be the event of getting a king. Okay, yeah, we're just picking one card, so there are 52. The sample space is 52 outcomes. How many ways to get a diamond? 13. So there are 13 cards of each suit. Okay, so the probability of E1, the probability of getting a diamond is 13 divided by 52. There are 4 kings, so the probability of getting a king is 4 divided by 52. Then we look at the intersection. So what's the probability of getting a diamond and a king? Well, there's only one card that's a diamond and a king, the king of diamonds. So one way for that to happen out of the 52. Alright, so the probability of getting a diamond or a king is the union. And by our formula, it's 13 plus 4 minus 1 over 52. That's 16 over 52. Cancel 4s, that's 4 out of 13. So there's a 4 in 13 chance of getting a diamond or a king. Alright, so that's the way that works. Yeah, using these two events. Of course, you could just count up how many cards are diamonds or kings. Yeah, you'll see there are 16 cards that fit the bill, and so 16 out of 52. But this is just a nice way to do it using our inclusion-exclusion principle formula. Let's see one last example. What is the probability that a positive number selected at random from 1 to 100 is divisible by either 2 or 5? So let's let E1 be the event that it's divisible by 2, E2 that it's divisible by 5. Okay, then union is being divisible by either 2 or 5 or both. The intersection means you're divisible by 2 and 5. In other words, you're divisible by 10. Alright, so now we can count each. The sample space here is size 100. 50 of the numbers are divisible by 2, so all the even ones between 1 and 100. Which numbers are divisible by 5? Well, all the multiples of 5, so 1 times 5, 2 times 5, up to 20 times 5. So 20 are divisible by 5. And we need to subtract the number divisible by 2 and 5. So the number divisible by 10, there are 10 of those. Alright, so we have our probabilities. So the probability of being divisible by 2 is 50 over 100. The probability of being divisible by 5 is 20 over 100 minus the probability of being divisible by 10. Okay, and then work out these fractions. See, we're getting well, it's 60 over 100. Cancel 20 is 3 over 5. So there's a 3 over 5 probability that a random number from the first 100 is divisible by either 2 or 5. 60% chance. Okay, so that's another application of this formula.